So we are on chemistry 12.5. We don't need the board for this one. All I'm going to do is read some papers. I could have done this one sitting down, but my director said no, the tripod would have to be adjusted, so that's not a thing. So here I am reading stuff from 12.5. So the top four answers that you're after are distillation, then probably distillate, but I might not be pronouncing that word right because I've only read it, I've never heard it. So I'm going to say distillate, but I don't guarantee you the accuracy of that pronunciation. Residue, and then fractional distillations. The basic idea on one for distillation is if you boil something, imagine you're trying to purify water, if you boil it and it becomes steam, none of the mess becomes steam with it. If you have water with impurity in it and you boil the water, the steam is pure H2O, and all the other mess that would be in there gets left behind most likely. Then if you could collect that steam somewhere and turn it back into water, you'd have purer water than what you started with. So that's a scheme to purify not just water, but that could work on any liquid. And the book has a picture of them doing that. They have something boiling, they send it through some tubes into another container, but when you do that, the water is called the distillate, and then the impurities left behind, that's called residue. That's what that thing is about. Petroleum industry, to try to purify their stuff, they said there's a thing called fractional distillations. It just means they do it over and over and over and over and over and over and over again, just to get it better and better and better and better and better. Well, that's our new words. If you're not feeling like you have a full grasp on 16 to 27, tune that in, 16 to 37, excuse me, tune that in. I'll read through that in a minute. If you need another run through to understand that better, I'll try to explain it in a new day, in a new way. But if you don't need that, you can cut the video in a minute here. What's up next on this is 12.6. 12.6 only has 2 new points. There's no mathy homework tonight. There's also no mathy homework tomorrow. There's no mathy homework the next day. It's going to be a while before you hit another mathy homework day. If you had trouble with last night's 13 to 17, email me and we'll set something up to try to talk over Zoom or do something to try to get some communication going to help you on the 13 to 17. Change of things today. Again, 2 new points on 12.6. Everything from 16 down that I'm about to read, we'll keep all that stuff the same. 5 through 15 today is getting cut. The quiz it got big fast yesterday. I understand you probably didn't enjoy that one, but we'll trim some stuff to keep these a little bit more manageable in size. So 5 to 15 is out, 16 and down is still in. Number 1 today will go backward tomorrow. What is distillation? So you would just go from purify to the end. Purifying a liquid by boiling it and then cooling the vapors. 2 and 3 is the same, still fill-ins. 4 is the same, still fill-ins. If you have a mastery of yesterday's words, just cut the video, live your life. If you don't quite understand yesterday's words and what they meant, I'll try again. So 16 to 27, we were contrasting condensation versus evaporation. So condensation's category is if you turn a gas into a liquid. So if you don't want to just blind memorize things, but you want to be able to reason them out, which is usually better, you could try to think through the process here. Gas particles have less energy. Have more energy, said it backward. Gas particles have more energy. They're in constant rapid motion. Gases, the molecules are just going bonkers. Liquids, the particles don't have as much energy. There's some, but not as much. So if we want to turn a gas into a liquid, if a liquid is our goal, one of the things on that was to have low temperature. Having low temperature is more likely to get you a liquid because the higher the temperature, the more energy is there. If we're trying to make a liquid, we don't want that energy there. That's going to be a low temperature. Part of that category was that it's exothermic, given off heat. Because if you have a gas with a ton of energy and you're trying to make a liquid that has less energy, it needs to give away that energy. It needs to go somewhere other than be its own. so exothermic heat release. High pressure also helps you on that club because gases like to sort of spread out. They fill the room was the thing we talked about, fill any vessel. So if you put pressure to try to condense, hence the name, a gas to make it smaller, you're going to turn that into a liquid. So maybe that makes a little more sense with a little more detail. The evaporation on the other category is just all the opposites. Evaporation is the escape of molecules from the surface of a liquid to form vapor. The highest energy particles are escaping. Not from the bottom, but from the top. You've seen water boil. It's not like the steam comes out of the bottom. It's coming from the surface. Low pressure helps you there because pressure is trying to keep things compacted. If you're trying to make a gas, they're trying to escape. So if you lighten up the pressure, that makes that easier. High temperature is obviously the way that's going to go. Okay, we're going to try to have something that's a liquid with not a lot of energy. We're trying to make it be a gas with lots of energy. We need a high temperature to give it that energy. When you do that, it's going to be endothermic. We have to have heat absorbed. You have this low energy liquid. You want to make it a high energy gas, you have to give it some energy. It has to take that energy in to enable it to escape. So maybe that makes some more sense. 28's answer was that the kinetic energy has to overcome the attractive forces. Ideal gases are like far, far, far away from liquids. Real gases act a little bit more like liquids because they're a little closer on that scale. Ideal gases have no attractive forces of the molecules. We learned that last chapter. But real gases, there's some attractive force. But we need, for that to stay a gas, we need for the kinetic energy to overcome that, and then it stays gassy. If you didn't have enough kinetic energy, then it's going to turn into a liquid because we just talked about that in the condensation process. Less energy means it's liquid time, so you need energy to overcome the attractive forces to stay a gas. Dynamic equilibrium was the rate of a forward process equaling the rate of a reverse process occurring simultaneously. It's basically one thing's happening at the same time the reverse is happening, and it evens out, and you end up essentially just treading water. One thing's pushing you this way, something else is pushing you that way, both people are pushing with the same strength at the same time, you'd be stationary, nothing really would be occurring. Vapor pressure has to be in some kind of a closed container as part of measuring vapor pressure. It's the pressure exerted by a vapor that's in dynamic equilibrium with its liquid state. It's in this turning process where some of the liquid's becoming gas, some of the gas is becoming liquid. It's not imbalanced in either direction. It's a constant process to be in equilibrium. And if you measure the pressure at that sort of a time, that's called the vapor pressure. Boiling point is the temperature where the vapor pressure equals the external pressure. The vapor pressure being what we just talked about, the external pressure being just around you in the room. When those two things are equal, the vapor has a pressure and the room is doing a pressure and they balance. That's where the boiling point can happen. Boiling point lower happens at high altitude, largely because there's less pressure there, as we described in the evaporation category of 16 to 27. Takes food longer to cook, which I think I explained that fairly in detail yesterday. 34 and 5, it's just from that table, these numbers. The heat required to evaporate 1 gram of a liquid at the boiling point and constant pressure, and then the heat required to condense a gas. And then the units for those heats, we had calories over grams and joules over kilograms. So you just kind of have to memorize those. Calories are friends with grams, joules are friends with kilograms. So, hope that rehash helps if you were misunderstanding yesterday. If you're still not getting it, email me and we'll talk another time. But that's it for 12.5.